Bueno, vamos a comenzar la tercera clase del curso de Machine Learning. Hoy solo tengo un avisito chiquito nada más, enfocado a los estudiantes de grado. Yo mandé un mail para tratar de coordinar un horario para juntarnos con el profesor la semana que viene en forma grupal. Traten de responder, voy a esperar las respuestas hasta mañana al mediodía y ahí queda definido el día y el horario de la semana que viene para juntarnos una hora con el doctor Sodré, un poco para charlar entre todos y aprovechar que lo tenemos acá presente y interactuar en vivo y en directo. Así que nada, solo eso. Laerte, quedas a cargo.
Gracias, Analia. Okay, so we'll talk today about regression and classification. There are several topics that I will mention today, and they are illustrative of the kind of technique that we use in machine learning. Yeah? Okay, let's start with regression. I have already mentioned in the previous classes what is regression in machine learning. It is the estimation of a continuous variable in contrast with classification, where the y variable is qualitative, one can say. Regression is a kind of supervised learning. Examples, for example, the estimation of photometric redshift. We can use a training set comprised, for example, by magnitudes. And if we know the spectroscopic redshift of the galaxies in the training sample, we can do a regression and we obtain what we call photometric redshift. I think that Vitor will talk a bit more about that later. Another example of regression, we can use, say, a training set where we have magnitudes and a redshift, photometric or spectroscopic, to estimate the stellar mass of a galaxy. This is also a type of regression. Regression is parameter estimation. So what we need in regression models in general is to estimate of the parameters of the model. And there are many regression models that can be applied. Well, there are simple ones like linear regression that certainly all of you know, kernel regression, KNN, artificial neural networks, and many more. In general, we can consider the algorithm a black box, and we can just change the algorithms and evaluate their performance and choose the algorithm that gives the best performance. In order to evaluate the performance of an algorithm, we should train the model with a test set, with a training set, and evaluate it with a test set. The test set can't be seen during the training set. Otherwise, it will produce biased results, okay? So, let's write the regression model in this way. We have the y variable, that is the value that we want to predict, the regressor, and in general, we have errors. Errors can have many sources. For example, we can have errors in the x variable or in the y variable. And also, we can have errors due to model inadequacy. For example, if we have, say, a curve like that, and we use a straight line to fit this curve, of course, you can see that this curve doesn't fit, is not well fitted by a straight line. So this will introduce a kind of error that is due to the model. This sort of errors I called epistemic errors in the machine learning literature. In order to train a model, we will need a cost function or a loss function. You will see both names in the literature. And the objective of the cost function is to measure the quality of the model fitting. And then one optimizer should minimize the loss function, usually by gradient descent or its variants. There are many variants of gradient descent. For example, I noticed that yesterday Vitor used the Adam algorithm. Adam is a variant of gradient descent. Okay, let's consider the problem of ordinary least square. I suspect that all of you know about this problem, but it's useful to revise it before continuing. So we have a linear model. This is a representation of a linear model. It's important to clarify that when we say linear model, the model is linear with respect to the parameters, not to the variables. I can have, for example, instead of x here, x squared, or x to the power n. This doesn't change the character of the model. It continues linear. So this is a very important point. Linear means with respect to the parameters. Okay. In general, in this sort of problem, the cost function is the sum of the squares of the residuals, the ordinary chi-square. So we can write the loss function in this way. If we have any measurements, the chi-square is defined as the sum for each data of the observed value minus the computed value squared divided by the square of the error. And during the minimization or the learning of the algorithm, we minimize this chi-square. Well, the linear model has an analytical solution that can be written in matricial form this way. Notice that although I'm using a straight line here as example, but I can have an arbitrary number of parameters. So I can have, for example, W0 plus W1 times X plus W2 times X squared, etc. Things like that, or other variables. In general, the learning in machine learning is done by gradient descent. This is the motor of the learning in machine learning. And as I mentioned in the last class, for example, we can iteratively update the model parameters by gradient descent in this way. The new value of the parameter is the old value minus the learning coefficient times the gradient of the loss function. For example, in this specific case of the linear model, for a single datum, we have this kind of expression. And if you look at the terms in brackets here, you see that it is the residual of the IS the of the ISMON datum. It is the difference between the observed value minus the computed value. And as the training goes on, these residuals decrease and converge to a stationary value. So, for example, as I mentioned yesterday, if we have here the data, and I start with arbitrary values of W0 and the W1, and as the training goes on, the parameters are changed so that in the end of the day we obtain the best fit line that can be obtained directly by this sort of expression. Here I show how the loss function changes with the iterations, with this kind of iterations of the gradient descent algorithm. It falls very quickly. You can see here very quickly the parameters arrive to a region where relatively close to the final solution and converge to it after a number of iterations. A very important aspect of regression is what we call regularization, and I will try to show to you now what it means. Well, in the ideal world, models should have the right complexity or capacity. I'm including these names here just for your knowledge, because sometimes you see this sort of nomenclature in the literature. Well, if the model doesn't have the right complexity, it can be too simple and then it's underfitting the data, or too complex. It is overfitting the data. For example, suppose that we want to fit a polynomial of degree m to a training set, and we will apply the fitted model to a test set. What happens if we use a model that strongly overfits the data? Let's look here at the right side of this slide. So we have here in red the points that you are able to see in this slide. The points that are used for training, and in green that you are not seeing, I suspect. We have green points here, 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 here. These are the test sets. So if we start with a polynomial of degree, say 1, we have for the train and test set this behavior. The cost function is here. For a parabola, the cost function decreases a lot and is here. For a polynomial of degree 4, here, and so on. You can see that for the training set, the loss function always decreases by gradient descent. But look at the behavior of the test set. It starts to decrease up to a certain value, then it starts to increase. Oops. And it increases strongly. This happens because the data is already being overfitted here in this region. The best solution would be a polynomial of degree 2 or 3, something like that in this case. A polynomial, say, of degree 8 strongly overfits the data. Well, what happens when with overfitting? What happens is that the parameters, they explode. For example, in the case of the previous plot that I just shown you, if we use a polynomial of degree 9, look at the value of the coefficients. They are enormous, and you can see that they alternate between negative and positive values. These are, look at the magnitude of this number, for example. They are very, very large. So, regularization aims to avoid this explosion of the parameters, and is a way to prevent overfitting. There are several ways to prevent overfitting, but I would like to mention two here. We can avoid overfitting, for example, by adding a new term to the cost function. So let's suppose that our original cost function was just a chi-square, and we can add a term that involves the square of the parameters. Of course, if the parameter is too large, the loss function will be too large also. So with this sort of constraint that we are imposing here, we will be able to restrict the values of W and then obtain a better fitting to the data, avoiding overfitting. we have a new parameter here, a new hyperparameter actually, that's called parameter of regularization. This additional term, its role is to penalize high absolute values of the weight. This type of model is called regression, and it has also an analytical solution that can be expressed in matricial form in this way. Very similar as if we put alpha equals 0 here, we have the solution for the ordinary least square. There's another way to do regularization that's called the lasso, least absolute shrinkage and selection, where instead of using the square of the weights, we use the absolute value of the weights. But the principle is exactly the same. Lasso prevents that the weights grow too much. Otherwise, the solution would be not good at all. Both the lasso and the ridge regression are an extension of least square. And in this case, least square is a particular case of both these methods. We can obtain the best value of this hyperparameter alpha, for example, using a procedure that we call cross-validation, that I will talk more about it later. And so regularization is useful when we have many variables, or if these variables are correlated. In this case, we use either ridge regression or lasso, for example. A very important type of regression in machine learning is what we call kernel regression. We have already seen what a kernel is. It's a kind of function that computes local means in the data space. And if you remember, the kernel has an important hyperparameter that is the bandwidth, and which measures essentially the width of the kernel. There are many types of kernel, as we have already seen. And let's see what is kernel regression. It's a type of local regression. Here's the definition. Y is a function of x, is the awaited mean of the values of epsilon I. This expression can be written in this way, and you can see directly from this expression that is a weighted mean of local values of y, where the weights are dependent of the kernel chosen, as shown here. In this plot, I'm showing the data points in black, and several kernels with variable bandwidth. And you can see that some, using some bandwidth, we have a good fitting to the data, and with the others we can have a very bad fit, as in this case here. So the choice of H is essential for obtaining a good result, and the H can be obtained by cross-validation. Another important and simple case of regression is KNN regression. KNN means the case nearest neighbor algorithm, and in this case, the Y value that we are looking for is the mean or a weighted average of the values of the K points closest to X. It's very used for regression and classification. It has one hyperparameter, that's K, and it implements the intuition that similar or close features in the data space X should have similar outcomes Y. When we talk about nearest neighbor, we need to talk about the distances between the points. And there are many kinds of distances that we can use. For example, if I have a point in d dimensions, we can use, for example, what we call the Minkowski distance, which is defined in this way. If the p-value here is equal 1, we have what we call Manhattan distance. If p is equal to 2, we have Euclidean distance. Since distances are involved between different features, it's important that the data should be properly scaled. Otherwise, we will estimate the distance that it doesn't make sense at all. The distance that we should use with the KNN regression depends of the type of the data we are using, on the dimension of the data, etc. We need always to do experiments to find the best choices for this kind of algorithm. Here, just to show you an example, I present a simple result for photometric redshift estimation trained with the 12 photometric bands of S+, having has the target in the training process this digital sky survey spectroscopic redshift. So we train using the photometry the algorithm to estimate the spectroscopic redshift. This sort of procedure is called the photometric redshift estimation. Look, KNN is not very accurate, but it's fast and it is very easy to understand. So I always recommend that you use simple models that you are able to understand, even if they are not very good and don't provide the best results. But anyway, they will provide a good baseline to which compare with more complex models. Okay. Here I'm showing the magnitudes in the 12 bands of S plus for a given galaxy. And this is what we call a kind of photospectrum. In the case of this exercise, I am showing here how the mean square error of the classification of the regression changes with the number of neighbors. And you can see in this case that the best number is about 20, something like that, which provides the best results. And here I'm showing in the case of the training set, the relationship between the spectroscopic redshift and the photometric redshift derived with this algorithm. Okay, let's consider now classification. Classification has several differences with respect to regression. First, well, the x variable, like in regression, can be real or categorical, but the difference is in the y variable, because the y variable is not continuous as the variables in regression, but otherwise it is indeed qualitative or categorical or discrete variable. Y indeed represent classes or labels, and we can represent we can have either binary or multi-class classification. For example, we can classify galaxies in 4 classes, for example, elliptical, lenticular, spiral, or regular. We can classify stars, for example, in 7 classes, O, B, A, F, G, K, M. We can have problems where we have only 2 classes, binary classification. For example, the detection or non-detection of a given object. A very, very, very important problem issue in classification is that the training set should be balanced. What I mean by that? Suppose we have 2 classes. we need to have, in order to do a proper classification, the same number of objects in each class. Otherwise, we will always bias the result towards the most numerous class. Okay, this is very important. Training set should be balanced. In the case of, let me come back. In the case of regression, the training set should be representative of the test set, the set where we will apply the regression. Otherwise, we will obtain biased results also. If you remember that in the first class I mentioned Bayesian methods, we talked about priors. In the case of machine learning, the priors are, say, inside the training set. That's the reason why the training set should be representative of the problem that we want to solve. Otherwise, we have biased results. In the case of classification, to avoid bias, we need to have balanced training set. Well, in order to do classification, we need to attribute values for the y variables. And we do that with what we call one-hot encoding. That means the following. Suppose that we have, say, 3 classes, like here. We give the value 1 to, and we will classify the objects in class A, B, or C, for example. If an object is of class A in the training set, we will write it in this way, 1, 0, 0. If it is of class B, we will write the target as 0, 1, 0. If it is of type C, we will write the target as 0, 0, 1. The same for binary classification or multi-class classification in general. This is what we will use in to feed the algorithms for classification machine learning. I have already mentioned logistic regression before. Despite the name, it is used for classification, and it is a very simple algorithm, not very good at all, but very useful to understand how many machine learning algorithms work. Let's assume that we have a training set with features x. X can be, for example, the full width half maximum of images, magnitudes, etc. And we want to use this training set to classify the object as a star, and in this case y is equal to 0, or a galaxy, y equal to 1. Logistic regression models the probability of an outcome be a galaxy using what we call the sigmoid function. The sigmoid function is defined in this way and is illustrated here. You can see that it is between 0 and 1. Here's the value of x. And that's why it's useful to estimate probabilities. And in the case of logistic regression, for example, in the case of a straight line, things like that, where we have 2 parameters, I should write W here, but I didn't. Only now I am noticing that I changed the notation. But we can define the logistic regression in this way. The probability of having x is given by the sigmoid function. So in the training set, we use the training set to estimate the parameters of the model. In this case, the beta 0 and the beta 1. And we later apply the same classifier to the test set to obtain the probabilities of the objects in the test set being or either a star or a galaxy. So let's see what is the. This is another very important point and shows a very important difference between classification and regression. So let's look what is the likelihood of the model parameters. The probability of 1 I will call P. The probability of 0 in the case of binary classification is 1 minus P. Let's suppose that a given datum has a probability pi, the datum y. We can write this to 6 in this way. Pi power to y times 1 minus my modern okay pi power to y times 1 minus pi times to the power 1 minus y. This is exactly, if you look carefully, oops, to this expression here. If y is 1, this term is 0, so this is equivalent to p. If y is 0, this term is 1, and we have 1 minus pi, like here. Okay, so we can write the likelihood of the training set in this way, by assuming that the data is independent, so likelihood is the product of all the probabilities of the individual data. So the cost function, if we took the natural logarithm of the likelihood, is given by this expression. This is what we call binary cross entropy, and is the likelihood used in classification models, mainly in binary classification models. And you can see that this is very different from the chi-square, for example, that we use in regression. This is an important difference between classification and regression. The type of likelihood or the cost function that is minimized in order to obtain the parameter values. So we can obtain the parameters by maximum likelihood. So when we want to do a new prediction for a value of x, we use directly the sigmoid function with the computed values of the parameters here. Well, we will obtain a result that is a number between 0 and 1. And we can assume that if the probability is larger than a half, the object can be classified as a galaxy. Otherwise, it is classified as a star. The point is that logistic regression is very useful only in problems that are linearly separable. Problems where we can put, say, have or a line or a plane separating different classes. Unfortunately, this is not the case in general. So in general, we need to use more complex classification procedures. In the case of binary classification, we can, looking at the training set, verify whether the classification produced by the algorithms is correct or not. So we can have true negative. True negative, for example, is a star that was classified as a star. True positive, a galaxy that was classified as a galaxy. False negative, a star that was classified as a galaxy. False positive, sorry, here's the counter. False negative, a galaxy that was classified as a star. And the false positive, a star that was classified as a galaxy. In general, we can use what we call confusion metrics to visually see what happens with the output of the classifier. In the confusion metrics, we have here the targets of the test set, stars and galaxies, and the predictions, stars or galaxies. And here we have the true negatives, false negatives, false positives, true positives. From these quantities here, we can define many different metrics. The most important metrics used in classification are these. Completeness or recall, for example, is the fraction of the true positives with respect to true positives plus false negatives. Contamination, the ratio of false positives to true positives plus false positives. Accuracy, true positives plus true negatives over true positives plus true negatives plus false positives plus false negatives. Efficiency or precision, 1 minus contamination, given in this way. And also another quantity that we call F1 score, that is given by this quantity here, that involves the precision and the recall. Recall is, in astronomy in general, we talk about completeness. People in machine learning use the term recall for the same concept. So this is the sort of method that we use instead, say, of the mean square error to evaluate the quality of the binary classification. Another way to evaluate the result of a classification is through what we call the ROC curve. ROC means Receiver Operating Characteristic Curve. This strange name comes from when it was invented. It was invented by the military during the Second World War to evaluate errors in the radar detections. That's why it has this name. And it is very useful to do decision making. The ROC curve plots the false positive rate here, the true positive rate here. An ideal classifier would have a solution here, but in general we have solutions like that. And as close the solution is to this point, so in this case the blue curve here provides a better solution than the green curve here. A random classifier that just provides random outputs would be here. Another important metric that I didn't include here is the area under the curve. So the area under the ROC curve can also be used as a metric for the quality of the classification. Sometimes we don't know what metric to use. So this is a choice that the user should do. We can, for example, try to optimize the completeness or the accuracy or F1. This is to be decided by the user by examining the results and what it is expected. Okay, there are many classifiers. I had already mentioned decision trees. It is useful both for regression and classification. And what a decision tree does is to segment the input data space in a number of simple regions. And the prediction for a new observation will depend on the region where the point will follow. In the case, for example, let's consider a classification problem, and I feed the decision tree, which is, say, 12 magnitudes of S plus, and if the magnitude in this photometric band is less than here should be color. It couldn't be. Probably this is the J minus R color, because this number is not for magnitude. This is a number typical of color. So this figure is wrong. Yeah? Anyway, if the color is less than 0.2, the object goes to this branch. Otherwise, it goes to this branch. If it went for this branch, we compare another color, and depending of the output, it goes here or here, up to the leaves here. In the case of classification, if it falls here, it will be a star, falls here, it will be a star, falls here, it will be a galaxy, and so on. The decision trees are interpretable, as we can see here, by the choice of the colors, that we can see explicitly how the algorithm is doing its classification. So this is very interesting because it's interpretable. The disadvantage is that it is not competitive. Compared with other methods, it has a very bad performance. However, in ensemble methods, when we combine many of these decision trees, they become very powerful. And for example, in bagging, random forest boosting, they are very good classifiers. So, although decision trees by themselves are not very good classifiers, in ensemble methods they are. Decision trees works by splitting rules, starting from the top of the tree. It has nodes, branches, and leaves. At level of the tree, the nodes are divided in 2 or more branches. I never saw more than 2 branches, but it's possible. This division is done according to a decision limit that is defined during the training process. After training a tree, we enter here with the values that we want to classify, and we see where it falls here in the leaves, and this provides a classification. Okay, random forest is a very powerful algorithm used both for classification and regression. And it is done by combining a large number of decision trees. They are a very important aspect of random forest is that it not uses necessarily all the features. For example, let's suppose that the data has m features. For example, if you are considering the S plus photometry, it has 12 features, the 12 magnitudes provided by the survey. But each of the decision trees here can use only a small number of these filters. So instead of using, say, 12 magnitudes, you can use 3 or 4 or 5. And we use, say, a fixed number m of features for each tree, and a larger number of trees. And the result will be either a mean or a combined value of the output of all these trees. This kind of procedure, where we use a smaller number of features than the original data, is very useful to avoid overfitting, and actually it improves the prediction. And again, these parameters, the number of trees, the number of features to be used in the random forest, can be chosen by cross-validation. A very important algorithm used for classification is support vector machine. let's look at the figure here. You can see that these two parallel lines here, they are defined as the parallel lines that maximize the margin. Margin is the difference between the extreme point in this class and the extreme point in this class, is this distance here. These lines are called support vectors. And the line in the middle is the line that maximizes the separation between these two classes. Unfortunately, in many classification problems, the classes are not so clearly separated. So we need to do some trick here to be able to use this sort of algorithm. And this is done by adding new features to the data in order to enlarge the feature space. In order to understand what happens, let's look at this example here. Let's suppose that the data, we have two classes, the blue class and the red class here. You can see that there is not possible to separate these two classes with any kind of line. This is not linearly separable. But if we introduce a new variable, say z equal x squared plus y square in this example, and plot z against x, you can see that now we have two classes that are linearly separated. We have the blue class here and the red class here. That's what the support vector machine does. In order to create new features, it uses something that's called the kernel trick, that uses kernels to look for the best separation possible between different classes. Support vector machines, together with random forest boosting, are amongst the best classifiers available. Okay, I have mentioned several times cross-validation. One very simple type of cross-validation I have already talked about. We can separate the data that we want to fit in two sets, in the training plus validation set and the test set. The training plus validation is used for the estimation of the model parameters and the model error, whereas the test set is used for the estimation of the model reliability. So we train the model and use the test set to evaluate the quality of the model. In order to have proper results, the test set cannot be used for training and validation. Okay, this is very important. Well, this is what we call simple cross-validation. Most important is the k-fold cross-validation. In this case, we divide the training set in several subsets. For example, in this case, we are dividing the training set in 4 subsets, and 3 are used for training and 1 for validation. And we exchange the validation in each run. And in the end, we estimate the error in the models by the median, for example, of the errors in each subset. We train the model here and they obtain an error using the testing set. We train the model here, obtain another error using the testing set. And after we compute the median of the errors here to obtain an estimate of the errors of the model. Let's consider, for example, how we can use cross-validation to estimate an hyperparameter. It could be, for example, the learning rate of the gradient descent algorithm, the regularization parameter, the K in KNN, whatever. What we do is to try several different values of alpha and choose the best model. One way of doing it is through what we call level and out cross-validation. It involves using one observation as the validation set and the remaining observations as a training set. And we repeat it for all samples of a training or validation set. So we estimate an error, and here, for example, you can see the the error in the say prediction in a classification or regression problem, and here the parameter that we are varying, say the alpha parameter, and we verify that there is say a minimum here, and this is the value of the hyperparameter that we adopt. Here is an illustration of how this algorithm works. We have the training set here. We have the x and y variables. And the output will be an estimation of the prediction error for a given value of alpha. And we will choose alpha that minimizes this function. Here I put a pseudocode. We start with error equals 0. And for each datum, we have any datum, we estimate, we remove one object. For example, if we are considering the object I, you can see that I go here from x1 to xi minus 1, xy plus 1 to xn. The same for y here. So we are excluding the ice object. And then we have, say, a machine learning model that I'm calling F. It could be anything. We estimate the value of y using this model without this object and estimate the error. And doing that for all the objects and with a fixed value of alpha, we obtain the expected error for a given value of alpha. That's what is plotted here. In this way, we choose the best value of the hyperparameter in consideration. Okay, I have included in this slide something that I find very useful, that are hints from the Chollet's book. Chollet's book is the Deep Learning with Python. And the Chollet's call it the universal workflow of machine learning. First, define the task. What is the problem to be solved? What is the data to be used? And this is the most arduous, time-consuming, and costly part of most machine learning projects, to choose the proper data. The data used for training should be representative of the application data. In the case of classification, the data we need to have the same number of objects in each class. In other words, we need to have balanced data sets. And well, in this stage of the process, we also need to define what kind of machine learning algorithms we will use, and how we will measure the metrics for success. For example, in classification problems, we can use the accuracy as a metric. In the case of regression, we can use the mean square error. Okay. After that, we develop a model. we pre-process the data. In general, we need to do it. For example, we need to do normalization of the data. We need to see what we'll do with missing data, things like that. We need to develop what Cholet calls evaluation protocol to evaluate the metric of success of your application. Select a training procedure and use a representative training set. It's always useful to start with a very simple model that establish a baseline. And then we will try to beat the baseline. So we first develop a simple and fast model to select the input variables, the algorithm configuration, the training strategies, things like that. Then we scale up the model. We can develop a model very complex that overfits. The ideal model is right at the border between underfitting and overfitting, as we have already seen. Said in other words, undercapacity or overcapacity. And we need to figure out where is this border. And in order to do that, we need to cross it. That's why we need to do a model that overfits. After doing that, we need to regularize or tune the model to maximize the generalization performance. And here also we have to lose a lot of time because, say, in the case of neural networks, we need to define the number of hidden layers, things like that. After all is done, we have a good model, we can apply the model. So we can analyze the weak points of the model if it produces biased results, misclassifications, things like that, and establish the resulting performance. Okay, now I let you with Vitor, who will show to you some applications of this procedure.
Uh, okay. Hi everyone. So this is Vitor again. I'm going to continue the practical class and talk about what I just told us about regression and classification. So in this notebook, I'm going to talk about two different methods to perform classification and two different methods to perform regression. I will not touch on the subject of cross-validation or missing data. I think I'll leave this to talk about tomorrow. So today I just want to give you a very first example of how do we classify and regress some things. So I think this will be quicker than the other classes, but I'll try to go over everything. So let's start with the classification problem. So classification task, as Laerte told us before, is used in many areas of science. So it's very common that we have some amount of data that needs to be put into categories, such as, for example, images of cats and dogs, or stars and galaxies, or whatever you want to classify. And so right here, we're going to use the MNIST. So I don't remember what exactly the acronym means, but it's a very well-known data set which contains handwritten numbers. So this is one of the oldest machine learning data sets because you can think about how to classify, for example. So this is just a bunch of examples from the MNIST data set. And you can start to think about, for example, how to classify each one of those numbers using a traditional coding method without using, for example, any machine learning thing. So it's very hard. It's nearly impossible for you to try to code something, for example, to take into account the lines, the shapes. You need so much time that it's not worth it. So machine learning is here to help us to solve problems like this, where simple coding, the usual traditional coding, it's very hard, but we can do this. We can solve this problem very easily using machine learning itself. And so to solve this problem, so the idea behind the MNIST dataset is we have, I think, 60,000 objects, so 60,000 images, and we have a very the same amount of data from each one of those is. So it's a balanced data set, which is what Laerte talked about before. In classification tests, you must make sure that the data set you are using is balanced, which is the case over here. So and we want to each one of those images, so each one of those small images over here, for example, the 0, has a specific label related to that image. So the 0, for example, has a 0 related, the 1 has a 1, the 2 has a 2. And you can see that for some images, it's quite hard to distinguish, even looking at the numbers that we know that they should be. For example, this 7 over here, I don't know exactly if it's a 7, if it's a 1. It's kind of blending the lines between what it is. So let's see how a machine learning method would solve this problem. So the first thing that we need to do is to download this data. Oh, and also just to quickly mention that I'm going to do this example for the MNIST images, but you can do this for any kind of image. So I try to differentiate between where I download the data, where I use the MNIST data, and where is the actual algorithm that you can generalize for whatever other problem you want, be it for star galaxy classification or any kind of classification that you want to tackle. So, okay, so the first thing that we need to do is to download the MNIST database. And since it's a very well-known database, there are a lot of machine learning programs that are going to use this as a baseline. It's already contained, it's already part of the TensorFlow library. So if you go to the TensorFlow Keras datasets, you will find a lot of different datasets, just like the MNIST. So there is the MNIST is one of them. There is the Boston housing dataset, which is information about the houses that you need to try to obtain the value of the house from information like the room, the number of rooms, the criminality rate, such as and other parameters. But MNIST is part of these datasets, and to download it, you simply need to write this line of code from TensorFlow import to MNIST, and then we will separate the MNIST into training and set data. So as Laerte told us in the class, I think yesterday, when he told about the different train tests separation. In this case, we won't be using the validation set. We'll just be using the train and test data. So we have a X train, Y train, X test, and Y test to use. And let's plot some images. So just the first 9 images of the, I think, sorry, it's it's the first 9 images of the MNIST database, just to see their looks. So you can see that each one of them has it's a 28 by 28 pixel image, and each pixel is a small square here that contains a value from 0 to 255, and this value is telling about how to paint basically the tile. So for example, the black can be 0 and the white can be 255. And so by mixing together those pixels, you can manage to create those images. And this is the first time that we're working with a 2D image instead of a single array. So I think yesterday, I don't think I remember if I put any problem using 2D arrays. So the way that we're going to deal with because we cannot give the network very easily a 2D array, usually models are very much familiar with one-dimensional array, so a single list instead of like a matrix. And so the way that we're going to deal with that is just that we're going to concatenate all of the other rows. So basically, we're going to do one big array to, and this is the cell over here. So we're going to transform each image, instead of going from 3D to like it's a two-dimensional image, we're going to transform it to a single array. And the way you're going to do that is by um, creating an array such that all of the data is like you you start at 0 and you go through the first line, and then you continue up to the second line, and then the third line is all concatenated into a single line. And okay, so this is a very important step to do. You need to do those kind of things. And the other thing that we need to do is, as Laerte mentioned before, we need to normalize the data. So these values are ranging from 0 to 255. And so to make them, let's make them fall into the 0-1 range, which is usually what the range of data that we want to work with. We usually want to work with data that is falling into the 0-1 range. And to normalize the data, since we know that the maximum value of each pixel can be 255, if you just divide each array, so the train data and the test data, by 255, we will actually manage to see if to make the predictions fall between the 0 and 1 range. Sorry, the pixels fall into the 0-1 range. Okay, so now let's see the first approach by a KNN classifier. So Laerte already talked about this, but I'm going to remember how it works. So the k-nearest neighbor classifier works. The idea is pretty simple. So it works much like the KNN clustering algorithm. So the one that I showed you yesterday. So the way the KNN classifier works is that you give it a set of data, some amount of data, some training data, and then you ask the classifier to classify a new point in that is not part of the original training set. And so what it will do is that it will place this point in in a very high dimensionality space, what we call the latent space. And so it will place this point in this space, and it will check all of the closest members, so all of its neighbors, and it will try to predict the class of this new object based on the class of the nearest neighbors. So if all of for example, if you take the 5 nearest neighbors, and you see that all of the 5 neighbors, for example, are a galaxy, so this image is probably from a galaxy. In the case of the MNIS, for example, if all of the neighbors are, for example, 9, then the image that you're passing is probably a 9. And so this is the idea behind the KNN the KNN classifier algorithm. And this is what we call a lazy model, which means that the KNN classifier instantly, it can basically train instantly. So when you fit the data into the classifier, it doesn't actually learn anything. It just knows, it just makes those points, place those points, the training set in the space. And when you actually ask the classifier to give you a new prediction, then it actually starts calculating something. But it's basically the idea of lazy model is that it doesn't actually train. It doesn't actually take any time to train. It just train everything instantly, because there is no actual training going on. So even though that the KNN classifier is quite simple, it works very well. So even the simplest model, such as this one, is going to have some very great results. So let's use this this model. We're going to use the class KNN neighbors classifier from the sklearn neighbors library. You can see that I think for yesterday's models and I think all of today's models are going to be using the sklearn library. It's because sklearn is basically the main machine learning library, the main traditional machine learning library. And just when we switch to deep learning for tomorrow class, we will be using another different kind of library. So it takes this method takes an initial argument that is the number of neighbors. So the idea behind it is that the number of neighbors is going to be the amount of neighbors I'm going to select to make this like voting system to decide which class is my new object from. So if I select, for example, a number of neighbors equal to 5, then when I place a new point in this space, it's going to take the 5 nearest neighbors and then see what those 5 nearest neighbors have a class, and we'll decide based on that. And so this is one of the hyperparameters. It can change, so you can go from whatever, like 0 to whatever is the size of the data set. And you can actually change this value and see the change in the. So basically you can optimize your algorithm based on the number of neighbors being used, and we're going to do that later. So after I just show you an initial application of the k-nearest neighbor classifier, I'm going to try to optimize it just so you can see how it works. So we're going to import this k-nearest neighbor function, and then we're going to create this this model by defining the number of neighbors equal to 10. I just put it out of my head. It can be whatever value you want. Again, we're going to optimize this later, and then you fit the data to the KNN model. And after doing that, we're going to be predicting and seeing the accuracy of the model. So to do that, we're going to remember the previous classes about when I talked about the metrics and the idea behind it. Now we're going to use the sklearn metrics, and we're going just to compute the accuracy of the model. We're not going to, for example, look at the F1 score. At least not right now. We're going to look at something like the ROC curve or the confusion matrix. We're going to look at it later, but right now we're just interested in the accuracy, the simplest metric that I can look, which is gives us that the accuracy of the model is 96.65%. So it's managing to classify those MNIST images correctly 96% of the time, and this is very good. This is for such a simple model. It's doing a very good job. Now, let's see if we can make it better by observing different values of the number of neighbors. Basically, let's try to change the hyperparameter of the model and see if we can change its values. So this is just a cell that's going to compute everything that I did before. So this is just trying to gather the same information that I placed before, but in a single cell, in a single loop, that's going to give us different ranges of number of neighbors. I'm just going to press F5 because before this class I changed some of the results, and just to show you right now that I'm going from 1 to 20. So basically from the so from 1 neighbor to 20 neighbors. And this cell takes quite some time to run. So if you try to run in your computer, it take about 10 minutes to run. At least in mine took that amount of time. And if you increase the number of neighbors, it's going to take even more time to train. So this loop is basically going through all of the possible outcomes, and it's trying to store here in the accuracy score list is going to store the value of the accuracy of each one of the different models, and we can see by plotting this list. So here we have on the x-axis we have the number of neighbors, so up from 0 up to 20 neighbors, and on the y-axis we have the accuracy score of the model. So you can see that for example, for 1 it's quite okay, but when you go to 2 the model is pretty bad, and then you go up to when you give it 3 neighbors, it goes up to I think 97.5%, and then it continuously go down. The idea is that if you give it a lot of neighbors, if you have a number of neighbors very large, you will basically try to randomly select, because you have so much data that you can actually be certain about the prediction. So as you increase the number of neighbors, the accuracy of the model should go down, and that's what we see. So in this case, the best value that we had was for just 3 neighbors. So it's computing only the 3 nearest neighbors. Will have you a 97% accuracy, and that's pretty good. So that we are, even though it's a very simple model, we were pretty good with that. And so I'll talk about right now another classification algorithm, which is the support vector machine. So Laerte mentioned it before, and this is a very high-level classification algorithm. So it is gaining a lot of traction in the scientific community. So especially for not even classification, but for regression algorithms, the support vector machine is being used a lot. And the idea is that, so as Laerte presented before, it's trying to create some divisions, like some planes and some lines, to divide the data by creating some other latent space. So by making a combination, for example, of the features. So the idea behind it, even though it's quite simple when you look at the image, the background is working. It's very robust, and it's doing some very heavy lifting here. But it's a very high level algorithm that we're going to use and see if it can manage to. Usually we would expect that the support vector machine would be better than the KNN, but let's see if that's what we actually see here. So and again, I'm going to only talk about classification, but this method can be used for regression too, as all of the methods that I'm going to talk about. Actually, I don't know about XGBoost, but I know that random forest regressor also has a random forest classifier, which you can use for as the same idea of the support vector machine. You can use for both problems. And so we're going to use the SVC, so basically the support vector classifier from the sklearn.svm library. So sklearn.svm is the support vector machine library that contains all of the possible support vector models, including the support vector classifier. And so here we'll make a kind of naive approach by using the default parameters. So SVM takes a lot of the SVC, the support vector classifier, takes a lot of different parameters, and there are a lot of things that can be changed, such as, for example, the kernel function, or the, if I'm not mistaken, the number of some number of iterations, for example, and by changing those parameters, such as the number of what is the name? The number of neighbors that we changed before, we actually can change the results, the output results. So the idea here is that I'm going to create a baseline model, such as Laerte told us previously, that we're going to run the simplest model just to see if things are working out and see the results. But you can change a lot of different hyperparameters by going. So this is by clicking this link, you go to the I think the sklearn.svm library, which will explain some of the kernels, and some of the right down the page you have some of the parameters that is trying to you can change. And so again, we use the default ones and see what happens. So in the case of support vector machine, it's the very same idea that we did for all of the previous machine learning methods. So you need to start your model, and then you need to feed some data to your model. Oops. You need to feed some data to your model. In this case, we're going to feed the X train and the Y train, the images and the labels. And then we're going to predict some values to the for the testing set and see what actually happens. So we can measure again the accuracy of the SVM by using the same function, the same accuracy score that we defined previously in the KNN neighbors case, and we see that we have an accuracy of 97.92%. So even though we're taking the simplest case possible, we're taking just the default parameters, it is already better than the estimation of the KNN. Even for the best KNN is not up to par as the kind of default SVM classifier. And yeah, that's pretty good. So that we were I was pretty impressed with that. A 92% accuracy is very high, but there are other ways to visualize the results. So one of the ways that I'm going to present, Laerte talked about the confusion matrix and the ROC curve. And in this case, I'm going to talk about simply the confusion matrix. So just to show you what the confusion matrix is so there is a method called, sorry, a function called confusion matrix from the sklearn matrix, which is going to gives us a you just input the prediction and the y-test, and it gives you something like this. So this is an example of the confusion matrix. Let me just zoom out so you can see it all. And okay, so it shows for each one of the labels. So for example, for 0, 1, 2, 3, etc., it shows you the percentage of the true positives and the false positives and false negatives. So in the case of, for example, let's say what you want to see in the confusion matrix is you want to see exactly as this. You want to see the diagonal, the main diagonal line as with the most amount of data. So you can see that all of the other tiles are around 0, so 0.01 or even 0. And so it is managing to classify all of the labels pretty well, despite there is no bias. For example, you could see in the confusion matrix if the classifier was classifying all of the images in the number 4 wrong. So you would be able to see that in the confusion matrix, which is not the case. I think one of the only the ones that are the highest is so this tile over here. It is the 2 and 7, so it's classifying the 2 and 7 quite wrong, which is kind to be, if you think about it, it makes sense. So the 2 and the 7 can be similar. So if you look at the original images, you can see that there are some number of 2's that could be somehow related to the 7, and that's the idea of the confusion matrix, to see those relationships in a visual way. And I think this covers the confusion matrix that I want to talk about. But you can also use the ROC curve, which is the one that Laerte talked about before, but I didn't plot it here. And now I want to talk about the regression problem. So in this case, regression problems are the ones that involves a continuous range of values to be predicted. So it's not a class such as before, that we had distinct values such as 0, 1, 2, and 3. Now we're going to be falling into a range of values. We can obtain any number inside a range. So for example, the height of a person, the temperature, for example, for tomorrow, or the photometric redshift of galaxies. In all of these cases, we want to give the model some amount of data and expect it to provide with a number that can fall into a continuous range. And in this example, we're going to use again, such as like we did in the yesterday class, we're going to use some real astronomical data. So this is the data that I currently use in my research, and I managed to just summarize it to make it simpler for us to run in the Colab. But basically, this is the data that we make science with. So this is we're going to be using a sample of magnitudes that are simulating the Southern Photometrical Local Universe Survey. So the S+ survey, Laerte commented before, is a photometric survey. So it is based on photometry and not the spectrum. They use a 12-band system, gathering information about the continuum with the broadbands and the spectral lines with the narrow band. So this is the filters that are having the S+ survey, and you can see that there are some filters, for example, that are very large, which are the broadband filters, and there are some filters that are very small. They're trying to get information from the spectral lines of the spectrum. And so we're trying to, so we have so the S plus survey is currently, I think it started in 2017, if I remember correctly. But we already have 3 data releases from the S plus survey, so which are public. The data is public, and it is trying to observe a range of different objects, from galaxies to stars to quasars, up to whatever object that you usually expect from a very wide sky survey. And so in this case, we're going to be simulating some S plus data, because we want to find a relationship between the S plus data, so the S plus magnitudes, the magnitudes that are coming from the observation from the telescope, and we want to correlate that to, we want to find a relationship to find the mass, the stellar mass of the galaxies, which is something that Laerte mentioned before. And so this data set is going to contain 137,000 galaxies, which are all in the stripe 82 region, which is a region of the sky. And for each galaxy, we have their S plus photometry and the redshift. So the redshift is just a measurement of the distance of the galaxy, and the respective stellar mass. And this data set was created by this guy over here. So the Ariel Werley, which is the one that I think I gave you a problem yesterday using the spectrum from this work, and yeah, it was the same data that we used from the last class. And so let's take a look at the data itself to have a better grasp of what we're talking about. So first we will download the data the same way that we downloaded before. So this is a Dropbox file, but you can place in GitHub or whatever you want. But by reading the data, we see that so there are a lot of different columns, and including with a lot of different names. And there is a few columns at the end, the Z and the log mass. So each one of those columns over here represents a different filter. So if you look, they are the same names. So the J0378, there is a J0378 over here. There you go. And so what we're having here is the same. So for each galaxy, which is for each line, we have their observation from S plus, and we have their redshift, which is the Z column, and the stellar mass, which is the log mass over here. And so we want to basically try to use all of this data over here to try to obtain the log mass, which is the last column. And yeah, so we're going to have 13 features, the 12 magnitudes plus a value of redshift, to obtain the stellar mass. And so I think that's clear. So let's go ahead and see how to do that. The first thing we're going to do is to separate the data between training sample and the test sample. So we will be using the train test split, which is a function from the sklearn model selection. And we're going to give us the data, all of the data excluding the log mass column. And as a target, we want everything. We want the log mass column as the target. And we're going to use a split of the test size is going to be 15% of the data, while the training set is going to be 85%. This is just an arbitrary number. Usually, we want a very high amount of training portion of the data and some relatively small tests. And so 85-15 is okay. And now that we split the data, we will be normalizing the data using a min-max scaler. So this is one of the possible scalars algorithms. So as Laerte talked before, we have a few different scaling algorithms, including the min-max scaler, which is going to transform all of the data between 0 and 1. So since the data doesn't have any kind of outliers, it's very balanced data set, it's very good. So we can use the min-max scaler just to put all of the data between 0 and 1. And you can also use the standard scaler, which is a scaler that we used in the previous class, which is going to try to fit, make your data fit into a standard normal distribution. But you can use whatever scaler that you want. It's going to change very little on the result itself. But if you want to try, you're welcome to do that. So okay, so and also one of the things that Laerte mentioned before is that it's very important to only scale only fit to the scaler the training set, and then we apply the scaled model to the test set, because we want the test set to be as close to a real observation as possible. So we're going to start by initializing the scalars, and then we're going to fit to the scalars the data. So we're going to fit the data and already transform the data to the 0-1 range. And this is going to be done to the X-train, so to the training features and to the target feature. And you can see that when I'm transforming the test set, so the X test that I want to apply to the model is going to be transformed using the X scalar, so the training scalar that I used before, because when we apply this to new data, we will be using this training scalar. So we want to mimic the what we'll be doing in the future. All right, so since now we have some already, we split the data, we have some we already scaled the data. Now it's just up to us to apply the regression algorithms. So first we're going to use the random forest regressor, and then we're going to use the XGBoost regressor. So the random forest is a very well-known algorithm. It uses, it has been around for a long time, and has always managed to prove its value. So you can go to archive right now and search for random forest. You will see some paper that came out like this week or last week. So random forest is a very good algorithm. It is based on the decision trees. So the random forest tries to understand how the data can be divided by making decisions based on its features. And the idea behind the random forest using decision trees is that we use a lot of decision trees, and you manage to compute like the mean or the average or the median of the decision trees to have a better grasp of the final estimation. And so since you can, of course, the random forest manages to compete with deep learning algorithms, which is what I talked before. And even though Laerte didn't show this kind of plot before, usually when you're talking about classical machine learning codes such as random forest or XGBoost, when compared to deep learning codes, there is a very clear difference on performance on the amount of data that you're using. So I think probably Laerte will talk about this tomorrow, but in the case of machine learning, classical machine learning codes, they perform much better when you have a lesser amount of data. So if you have a small data set, for example, usually the random forest regressor or XGBoost is going to perform better than other deep learning algorithms such as neural networks. And so one of the other advantages of using an algorithm such as random forest is that it is very easy to interpret the network. So as Laerte showed before, the decision trees, and you can see the decision splitting, you have a very good interpretability of the network. And okay, so to actually use the random forest, we're going to use the sklearn ensemble library and its random forest regressor model. So this algorithm takes a lot of important parameters, but the most important one is the number of estimators. So if you look at the documentation, I think the person writing the documentation wanted to have some fun. And if you look at the description for the number of the estimators, it is very referred as the number of trees in the forest. So this is actually a quote from the documentation, and the idea is that the number of estimator is going to dictate the amount of decision trees that you will be computing. So the higher the number of the decision trees, the better the algorithm will perform. But the problem is that you have like you need to balance it out, because you can't just choose a very high number of estimators, and because then the model will take a very long time to train. So you need to choose a number that is quite optimal. So for example, the 100 estimator, which is the default from the decision trees, we will already take, I think, about 3 minutes to train this model. If we increase, for example, for 400 estimators, then we will increase a lot the training time. And So you need to make sure about you all need to consider this balance. Up to when can you choose a number of estimators? Okay, so you can also check the other um, parameters from the random forest regressor, include, for example, things like how to make the decisions, and there are a lot of interesting parameters there. But I'm going just to talk about the number of estimators. Okay, so how to use the random forest regressor itself is just it's the exact same way as we did every other parameter. So you have the random, you initialize the model, so the random forest regressor, by defining the hyperparameters, which in this case is just the number of estimators that I'm going to choose as 100. And then we fit the data, the data itself and its targets, the features and the targets to the model. And then we want to predict for the test set, and we want to scale it back, because remember that all of this data is scaled. So when we make a prediction, we want to predict a value. So we want to predict the test set, and then we want to actually compare this to in like real physical values. So we want to scale back the predictions by using this inverse transformation. And okay, so let's look at some metrics for after the random forest has already fitted. Let's look at some metrics, and we're going to look at two different metrics: the root mean square error and the R squared. So these two metrics are used when we have both the predictions and the target. So when you're dealing with a supervised learning algorithm. And in this case, the idea of the R square is a metric that goes from 0 to 1, and the higher the better. So the closer to 1 it gets, it's like an attempt to have a notion of accuracy when you talk about regression. Even though it's not accuracy, the R square is trying to mimic the accuracy. It's going from 0 to 1, and the higher the better. And we are also going to look at the root mean square error of the network, which is the basically the general error of the network is going to for each one of the predictions is going to compute the difference between the value that we obtained minus the value of the that we should have obtained, and it's going to do some calculations based on that, and then it's going to output some kind of error, which is the one that we obtain here. So the lower the error, the better. That's the idea. So we want high R square, and we want low RMSE. And in this case, we have very high R squared, and we have some quite low RMSE. So this model is managing to regress very well. Is learning very well the relationship between the magnitudes and the stellar mass itself. And so, but even though we can see that the results are pretty good from these metrics, is there a way to visualize this prediction? And yes, there is a so-called prediction plot, which is that we will plot. So it's this image over here, which is, I'll explain the code later, but the idea behind it is that we want to have on the x-axis, we have the prediction from the random forest, and on the y-axis, we have the targets, the original value. And we want every single value in this plot to be over the one-to-one line, which is the red dashed line. And so we're going to use it's a very simple plot to do, but it's very useful for data visualization. So you can actually see that the data is almost perfectly falling in the one-to-one line. So there are a lot of outliers. For example, the data isn't having some kind of divergence, for example, for lower mass. So, and remember that this is the x-axis and the y-axis are representing the mass of the galaxy in the logarithm scale. So, for example, for lower mass galaxies, you see that the model is not performing that well, probably because we don't have a lot of data over here. But for some average mass galaxies, the model is performing really, really well. And yeah, that's what you see from the prediction plots. And this is a very useful tool when you want to visualize the results. And so yeah, so okay, so we were pretty happy with that. We had some very good metrics. We had some very good predictions. And so let's compare this model to another model, the XGBoost. So the XGBoost is a very kind of new algorithm. I think it was published in 2014, if I'm not mistaken. XGBoost itself, the idea of gradient boosting has been around for some time, but XGBoost itself is quite recent. But the idea behind it, so the name of the thing is the extreme gradient boosting algorithm, XGBoost. So it's one of the methods that it's gaining popularity a lot, not just in general areas, but especially in astronomy. If you go to arXiv again and look up machine learning papers, you will see a lot of XGBoost papers. And it is based on the gradient boosting method, so which is essentially an ensemble of decision trees. So as Laerte mentioned before, decision trees are not necessarily being used only by random forests. It can be used for by many other algorithms, including XGBoost. And in the case of XGBoost, it uses what is called some weak learners. Weak learners are so when it tries to fit some data into, it tries to manage to get the idea of the prediction that you want, the relationship that you want. And then it's going to look for the weak learns, which are the decision trees that do just slightly better than the random chance, just slightly better than the average, for example. And so it will take those decision trees and it will look at the gap that was left by the other decision trees. So, for example, if this weak learner, for example, manages to compute to have a very good idea for, I don't know, maybe 30% of the data, then it will take it will train another decision trees or other decision trees to fill this gap, so to fill the other 70% that was left, and it will do for a number of times, and in the end you will have an ensemble method, basically like a combination of different decision trees that each one individually couldn't have a grasp of the relationship, but combined they have a very good idea of what the relationship is. So one of the problems with the XGBoost is that it sacrifices the interpretability of random forest, but increases the performance. So it's a little bit hard for you to interpret the decision trees in the XGBoost algorithm, because it's not as clear as the random forest one, when you can look at the decision trees because there is just one single decision tree that you had. In the case of XGBoost, you will have an ensemble of decision trees. So it's hard for you to look at all of them and have an idea of what exactly is going on with the network. This one works like a black box that I mentioned before. And to use the XGBoost, there is a library for that. The library is called XGBoost itself. And so we can easily see the performance by using this library. So the regressor itself is the XGB regressor, so the XGBoost regressor function. And just like the random forest, the only parameter we need to set is the number of estimators. But there are a lot of other hyperparameters in the XGBoost function. And I truly recommend, if you're going to use XGBoost to your project or whatever you want, I truly recommend you go to the XGBoost documentation and see all of the parameters that just to show you. So you have the number of estimator, the max depth, the max leaves, the max bin, the growth policy, learning rate. You have a lot of things that are important for the regressor itself. But I won't be focused on that right now. So I'll just focus on the single one, the number of estimators, and see how that goes. Basically, it's the same naive idea that I applied before. I will try to run a baseline model and see how it goes. And you can see that in this case, I managed to increase the number of estimators to 500 because the XGBoost algorithm was quicker than the random forest algorithm for this case over here. And so we increased the number of estimators. We called the XGBoost function, the XGBR regressor, and started the model. And then we feed the data to the XGBoost model. And you can see that for all of the machine learning methods that I talked until right now, it's always the same pipeline in Python. You usually will get the model from a library. You will start the model, so you initialize the model, and then you feed the model to some data, and then you predict the model through the training set. So it's always the same pipeline. That's what I want you to see. It doesn't matter what model you choose, it will most likely be something very similar to that. And so for predicting then we will predict for the test set, And again, we need to predict the data and scale it back, because the prediction is going to be between 0 and 1. And we want the network to, sorry, we want to compare the results in a physical range of the mass. And so let's look at the R-squared and root mean square error. So we had an R-square of 98% and a root mean square error of 0.097. And if we compare both the R-squared and the RMSE for when compared to the random forest regressor, you see that the values are very similar. You have 98% and 0.096. Is because in this case in this case, the random forest regressor and the XGBoost regressor are managing to find this relationship pretty easily. So it's managed to compute the relationship very well, and so that's why we don't see a lot of difference between the R-squared and the RMMSE for different methods. If you look at another database, if you try to apply this problem for other problems, if I try to apply this method to other problems, you'll probably see some difference between the XGBoost and the random forest regressor. And so again, let's plot the predict plot that we had in the same case as the random forest, and you can see that's very similar shape. So you can see that the scatter is a little bit lower in the higher regions of for higher masses when compared to the random forests over here. You have a little bit more scatter, but again, from the metrics you see that overall there's not much difference. Like you gain in some places, you lose in some others, and overall it's all the same. And so yeah, that's how you use the XGBoost prediction. And I think that's it. That's what I want to talk about the regression itself. And we try to leave you guys with an exercise. And here we want to predict the galactic redshift from the photometric data. So usually we call them photometric redshifts or photo-Z's. So whenever you have a redshift estimated from the photometric data, we will use again the S plus survey magnitudes that were the same way that were described before, and it's all easily available in the dataset that I left you guys with. And so for this, I think I don't remember the amount of data there is in this dataset, but basically what we want you to do is to use all of these features over here, all of the spectral magnitudes, and we want you to output the target of the model is the ZSDSS. That's the target of the model. And so we wanted you guys to use two different regression algorithms. So it can be random forest, it can be XGBoost, it can be KNN regressor, it can be SVM regressor, whatever model you want to predict the redshift from by combining all of the other features. And after that, we want you to compare the results and see which model performs best. So in the case of the stellar mass, even though there wasn't much difference between each different model, in the case of the photometric redshift, you're probably going to encounter a very clear difference between the whatever two models you use, be random forest, XGBoost, KNN, or whatever other model you find online. There are a very large number a very large number of regression algorithms that you can find online, and by simply searching on Google what available regression algorithms you have in Python, you can choose whatever you want. And I think that's it. So thank you for listening. So, questions for me and Laerte?
Questions?
I can start with a question to Laerte. Because I was interested in something that he talked about before.
Go ahead.
Laerte, when you talked about the I think it was in the when you talked about the different distances in the KNN classifier, the KNN regressor, you talked about two different ways to measure the distance: the Euclidean and the Manhattan distance. There are different values. Do you know when to use each one of them? What are the difference between them? Or
The Manhattan distance, there are different uses for these two distances. In most of the problems that we use the Euclidean distance, but there are occasions where the Manhattan distance can be better. I never used it, but I know, but I have seen that there are occasions when you should use it. For example, in optimization problems, when you have discrete variables, things like that, discrete input values. Because if you look at a graphical representation of a Manhattan distance, it is like a zigzag curve, whereas the Euclidean is more continuous curve.
Thank you.
Any other questions? ¿Otras preguntas? Bueno, agradecemos entonces a Vitor y a Laerte. Y abajo está el café, si quieren disfrutar un poquito. Gracias por venir.